For this Physics 1211 lab, I will be covering the discussion around a falling object and the concepts that are associated with it. So to introduce the main concepts that are associated with the idea of a falling object is that a falling object is modeled with two different types of forces. So the net force is going to be equal to the force of gravity plus the drag force. And basically these two forces will counteract one another. So one will be moving the opposite direction of another. So gravity will generally be moving downwards while drag will be pushing upwards. The second concept that is important is Newton's second law, which is final velocity is equal to initial velocity plus the net force divided by mass times the change in time. So this demonstrates that constant velocity is equal to a zero net force. And with the falling object, if there's a zero net force, the gravity force and the drag force, as labeled above, will cancel one another out to create a net force of zero. A net force will not be zero for the entirety of this experiment. However, with terminal velocity, it will reach zero in theory. So we will cover acceleration in this experiment because velocity will change throughout the course of the experiment. So first I'm going to discuss the tracker I used. So it revolves around dropping an object. I dropped a plastic cup with a diameter of 0.057 meters and a mass of 0.015 kilograms, and the object will move down the y-axis. So, as demonstrated in this experiment, you can see with this graph that due to there being a curved line and not a linear line, since the velocity will be the derivative of the position versus time graph, as shown in the bottom graph, we will ignore the x-axis because we are only focused on the y-axis for this experiment. The line is not linear, and therefore the slope of the curve will change, meaning a changing velocity throughout the experiment. For the computational models, I created one model that accounted for drag force and one that did not. The two major changes I made within my code were that without the drag force, I simply used the equations from the first lab, and then I added in the weight equation, which is the negative mass of the ball times gravity times the direction vector, which was downward. And then also, I created an F net equation that was equivalent to the weight. For drag, I had the weight equation, and then I also had a drag force, which is modeled by the equation FD, the second equation in the bottom one. And this was shown with the negative b value times the velocity of the ball. This meant that F net would now be W plus FD, or the weight plus the drag force. For the comparison of the results, the model with drag was much more accurate to the tracker video than the model without. So as you can see in this chart to the left, the first column in purple is the time, and then the second column is going to be the computational model without drag force. The third column is the actual tracker video, and then the fourth column is the computational model with drag force. As shown by the graph right here, in gray is the computational model with drag force, and in orange is the tracker video. So they are much closer to one another than the blue line, which is going to be the model that has no drag force. What does this mean? So, velocity versus time with and without drag have to do with terminal velocity. So, I believe the drag model predicts a better terminal velocity because it is closer to the actual model. As showed in the last slide, you see the orange and gray lines are closer to one another. And then also, the terminal velocity equation has to do with drag force. So the terminal velocity equation states that an object with a higher surface area will fall slower due to greater drag. Terminal velocity occurs when drag is equivalent to gravitational force. Therefore, the net force will equal zero. If an object was initially thrown downwards, the terminal velocity would eventually be the same as drag works against the object. This means that mass times gravity would have the same would be the same, and drag force would eventually be equal. Because velocity is included in the drag force equation, drag is proportional to velocity. This means it may take longer for the drag force to reach a higher number. I created a computational model of this to prove this by giving the object an initial velocity greater to 0 in one of my codes. So, to the left, my computational model is without an initial velocity. As you can see, it levels off faster than the one to the right, which is still decreasing at the end because there's an initial velocity greater than 0. That is all for this lab. Thank you very much.